Yeah. So, okay, let's start. So last time we had a very basic idea of radiation and pulses and basically how to think about time scales and how to think about time and frequency and how would like to think about averaging or taking some average energy in the pulse average spectrum which will be used later on. Today let us go back and start on the theory of radiation and all this pulse and stuff that I said, it will come back to us at a later stage. Okay. Now to start the theory of radiation, let us start again from the very basic. So start with potentials and gauges. Start with Maxwell's equation. Okay. So if I start writing down Maxwell's equation, writing down Maxwell's equation, then we'll write write down the curl of E is del T and divergence of B is 0. And along with the Maxwell's equations, we also have the local conservation law, which is divergence of J plus del T is equal to 0. And this is basically not an independent statement. So this is the conservation law. Is not an independent equation derived from the above. So if you take the first two equations, you can basically derive the conservation law. Okay. Now you also introduced
Sir,
yes.
sir, why are you talking only about one conservation law? There is another like a divergence of S plus du dt is equals to 0.
This is the local charge conservation law. Which conservation law are you talking about?
Yes, that's I am talking about. Why you are talking only about charge conservation law? There is an also energy conservation law like.
No. Okay. There is many conservation laws in that sense. There are many conservation laws in that sense. This is a local charge conservation law. This is derived from over here. The other conservation, there's all, of course, there will be energy conservation, there's a momentum conservation, there's an angular momentum conservation. Those are all standard conservation laws that is there. This is a specialty of EM, that there is a charge conservation law. And this comes just as a consequence of the previous equation. I mean, you can write down the other conservation laws. I mean, we have done whole classes on conservation laws. And when you talk about charges, you talk about charge that the charges is concerned, right? It's not created. That's the only conservation law that I'm talking about over here. Because whatever we do is basically about charge and fields, and the others are more of a dynamical conservation laws.
Okay.
I mean, there is nothing special about this or non-special about this, except you start with this 4 plus this 5 equations leads to other equations that comes in your standard EM theory. And the other conservation laws are system conservation laws that comes from the fact that, whatever we have done before, that this will be conserved, this will be, and those conservation laws are also valid for non-EM things. For EM, this is a special one, the charge. Remember that this charge conservation laws was, related to gauge properties. So we did something like the local conservation and the total charge conservation, these two things. Now, of course, when we talk about these equations, we also introduce potentials. So we introduce these potentials. I'm just writing all these things just to be, to be complete over here. So one of them, of course, is given by this equation. So we introduce the vector potential, and we have the scalar potential. Okay, so these are two potentials. So we introduce the potentials. A and phi. And then we also know that if I change the potentials in a particular way, then this B and E do not change. So we can make this transformation. So if A is changed to A plus some gradient of some scalar function lambda, and at the same time you also change phi, okay, and phi is changed to phi minus 1 by C del lambda del T. So if you make these changes, then there's this new set of potentials. So we get new set of potentials, okay, but the E and the B, but E and B, which are the physically measurable quantities, the physically measurable quantities, they remain unchanged. Okay. So this arbitrariness of the potentials is called gauge freedom, and this change that I have done is called the gauge transformation. So we have something called gauge freedom, which basically tells you this arbitrariness of the potentials, okay, and this thing is called gauge transfer. Okay. So this is a thing that we have done many times before. Now, if I want to put this gauge transformations into the first sets of Maxwell's equation, then if we put the gauge transformations in the Maxwell's equation, in the equations, and then simplify, then what we'll find that we are going to get equations which will be like the wave equation. So what we are going to get is this. So now, so we have the Maxwell's equation. So curl of B over here, B is curl of A. Okay, this E will be in terms of your A and phi. So basically put it over there. Okay. So you have a curl of curl of A, this is the curl of B. Then your E will be in terms of your A and phi. So 1 by C del T of minus grad phi minus 1 by C del A del T plus 4 pi by Cj. This was the first equation. Okay. And then this can be simplified further. Okay. So this or minus that's del T2 A and this. So I have used the properties of A cross B cross C, those properties. Okay. And this becomes minus terms of A plus 1 by C del phi del T plus 4 pi by Cj. Okay. And similarly, also from the second equation over here, from the second equation, okay, you can write down also from divergence of E is equal to 4 pi rho, you can write down minus grad squared phi minus 1 by C del T of divergence of A is equal to 4 pi rho. So let me actually look at these two equations. One equation is this, the other equation is this. So till now, whatever we have done before. So we have a pair of coupled second order differential equations in A and phi, right? So a pair of coupled second order differential equation in A and phi. So to solve for the fields, we need to solve this coupled pair of differential equations. Okay, because you need to fit A and phi, and once you know A and phi, we can find our E and B. Now, these things, if I want to solve it like this, of course, it's complicated. So one of the things that we can do over here is basically we use gauge freedom. So we make some choices. So we put some restrictions on the quantities and then try to see how those restrictions will help in simplifying these equations. And then if it simplifies, then of course it makes easier to solve those equations. So we talk about these restrictions, which are different or common choices of gauge. So we use to simplify, we impose what is called gauge choices. So let us look at the first gauge choice. Okay. The first gauge choice is known as Coulomb gauge. Okay. So there's something called the Coulomb gauge. So you always make mistake with the spelling of Coulomb gauge. It's called the Coulomb gauge or radiation gauge. So what is this? This is, so we impose this choice. So your divergence of A is equal to 0. So when we do that, as you can see what happens over here, the divergence of A part in the two equations goes to 0. So we end up with then we get minus grad squared phi is equal to 4 pi rho. and minus, so let me introduce the, okay, I'll do that. So we introduce this. J 1 by C del del T of minus K. Where I've introduced this symbol, which you know is called the D'Alembertian or Lambertian. There is no D pronounced actually, the Lambertian, which is anyway. So the whole point is we get two equations which are simply, and you can understand why it's called Coulomb gauge, because the first equation is the electrostatic equation, basically Coulomb's law. Okay, this is the reason why we call this the Coulomb gauge, because you end up with this minus grad squared phi is 4 pi. Now, if I look at the second one, the second equation, look at this second equation, then if I look at the right hand side of the second equation, so look at the RHS of this equation. Okay. So look at the RHS of this equation, then I can slightly modify this RHS. Okay. So what I can do is I can write it like this. What I can write is divergence of, so this was the J. So I'm going to basically take this 4 pi and C together. So J minus square of, so let me try to del phi del T. This becomes divergence of J minus 1 by 4 pi del del T of grad squared phi. This divergence of J plus del rho del T, and this is equal to 0. Okay. So in the way that we have actually used this Coulomb gauge is basically a way of saying that we have local charge conservation. Okay. So the last equality is from charge conservation. So basically, which means that if I write down this D'Alembertian again, okay, because this thing is 0, so I can write down this D'Alembertian, therefore, so minus the squared of divergence of, if I write down this thing, this part is 0, of course, 4 pi by C, divergence of G minus 1 by 4 pi. This has to, there has to divergence over here. It's, del phi del T. So when we put in this condition, we did not put in the condition arbitrarily. So of course we put a condition which made these things easier to solve, but it was something which was related to the physical uh, uh, state of this EM theory, that locally we conserve charges. So this is not an arbitrarily by hand condition. There is another gauge that is often used, which is known as the Lorentz gauge. So this was the Coulomb's gauge. Similarly, there is another gauge, which is called the Lorentz gauge. Again, if you look at the Lorentz gauge, it is again from over here. So look at this equation. So in the second, in this first equation, on the right hand side, there is a divergence of A plus 1 by C del phi del t term, right? I can put that equal to 0. Okay. So in the Lorentz gauge, what we impose divergence of A plus 1 by C del phi del t is equal to 0. This is actually an even nicer gauge because it simplifies the equation even more. So once we put this, then what we get, two equations. One equation is this Lambertian of A, which is equal to 4 pi by C times J. So this is a vector equation, okay? And the other equation is now the Lambertian of phi, which is 4 pi by C, which is 4 pi, there's no C over here. Okay. 4 pi rho. So these are two very simple symmetric equations. Okay. Remember previously what we got was the 3 divergence. So it was the grad squared phi as 4 pi rho. Over here is the D'Alembertian of phi is minus 4 pi rho. So this is that difference. It's not exactly the same as the previous one, but this is a completely symmetric equation. So in fact, this can be written up in 4 vector form much easier if I want to do that. So we can write down the Lorentz gauge as a 4 vector notation, and then this equations will be very easily written in a 4 vector notation. Now over here also, see that, you know, if I do this, I take the Lorentzian of the Lambertian of plus 1 by C del phi del t. Okay. Remember, this part is 0, so it has to come 0 on the right hand side also. This is nothing but 4 pi by C divergence of J plus del rho del t. So again, this means there is that charge is conserved. So in this way also, we can think of a conservation of charge over here. Now, depending on what kind of problems that we are going to do in EM theory, we either use this gauge or the other gauge. For radiation, it's always better or always easier to use your Lorentz gauge. One thing that I must emphasize is that the final answer should not depend on the gauge. Okay. At the end of it, you have some physical quantity, E and B, that should not depend on the gauge. Your gauge will only make your equations simpler and easier to use. So you choose a gauge, whichever you want to, so that you get some equations which are easier to work with, or maybe more intuitive to work with, depending on what kind of problems that we have. Now, for radiation, or radiation from moving charges or whatever. Whenever think of radiation.
Sir, I had a doubt.
Yes, Vishal.
Sir, is there any restriction on choosing the gauge? Means how can we choose the gauge? Means by random, means by any random combination of vector potential and that scalar potential.
Yeah, in the sense like it's so you could have, so whatever I'm doing now, for example, let's say I'll be showing you some example, or I'll be using the Lorentz gauge for calculating something. You could have calculated it without the Lorentz gauge and using a Coulomb gauge. But what would have happened over there is that your equations would become very cumbersome.
So,
So-
my question was that if I can choose that del phi upon only that del phi upon del t is equal to 0,
Which one?
that means if
Only
I
one-
make
1 by C del phi del t equal to 0.
yes.
Oh, but then it will be unphysical because then you will not have local charge conservation.
Okay, yes.
So now let's see where we can use the Lorentz gauge. And whether we can give, whether this gives some equations. So let us use Lorentz gauge in radiation. So use of Lorentz gauge. Radiation. So what we really mean to do over here is we're going to basically go back to solving Green's function. So remember we had basically talked about Green's function, and we are going to now basically do the same thing, Green's function, but an extended variety of the Green's function that we did, that we introduced in the last or the one class before, and solve it using Lorentz gauge. Okay, so what is the Lorentz gauge, Green's function using okay. So we want to solve these equations. Okay, these are the two equations. So we want to solve these equations. So we want to solve, let me call this I don't know, equation A. To solve equation A. Now, if you look at this equation A, for example, look at the second equation, the D'Alembertian of phi, which is 4 pi rho. This is exactly like the Coulomb equation that you have solved before, right? Which is you have, instead of a D'Alembertian, you have a grad squared phi and you have a 4 pi rho. And that grad squared phi 4 pi rho was solved using a Green's function, where we had the Green's function and we have the charge density distribution. So we integrated over the charge density distribution if you knew what was the Green's function. The Green's function was basically the solution for a point charge. Right? So we know how to solve using Green's function in 3D. What we're going to do is that we're going to solve the same thing by just extending it to 4D. So this, instead of grad squared phi is equal to 4 pi rho, we now have a Lambertian phi is equal to 4 pi rho. So instead of a 3D Green's function, which was only x, y, z, we'll have a 4D Green's function, which will be x, y, z and time, right? So back to your Green's function notes and see how we wrote phi in terms of the 3D Green's function. Over here, the solution in terms of Green's function will be, the solution will be solution similar to 3D Green's function. The solution will be now will be phi at R But now this has time also. So now we have a phi of r and t, which in the case of the 3D, we have to integrate over the volume. So d cubed r prime, because prime is the source and we want to find what is at r. So r prime is a source and I want to find what is at r. But now I have to have another variable, which is the dt prime. And then I will have a Green's function. Previously, it was just r minus r prime. Now it will also have a t minus t prime. And then I will have a density, charge density, which again previously was just r prime. Now it will also have t prime. So this is a straightforward 4-dimensional extension of the 3-dimensional solution. So now my charge can change not only with position but also with time. And so the potential at a distance at some other point will also change with time. If this is the case for the scalar potential, if you look at the form of these two equations, then the solution for the vector potential is exactly the same. Okay, it's very, very similar. So the solution for the vector potential will be ART integral dqr prime dt prime then g r minus r prime t minus t prime, and instead of rho now I will have a j by c, right? It should be 1 by c j r prime t prime. And just like the 3-dimensional Green's function was for a delta function charge, point charge, just in space. Now it will be a point charge in space and time. So delta function will be, instead of a 3D, it will be a 4D delta function, where this g, which is a function of r minus r prime and t minus t prime, this will be 4 pi delta 4 pi delta of r minus r prime and delta of t minus t prime. So this is the 4D generalization of minus gets but right. So this is what we have. Now we want to solve this. So we want to solve this equation. Now we want to solve this this equation. Okay, this. So we want to solve this equation. We want to solve this, and this we can solve this equation. Then phi and a is just integral over this 4 coordinates. Okay. So I don't know. Let me call this equation something. Okay. So we to solve the 4D g function equation. Now, to tackle this kind of equation, it is better that what we do is that we use a representation of the delta function. So if one of the delta functions can be used as a representation form, then it's easier to deal with the other delta function single. Okay. So what we want to use over here, I want to use. So this you can find in books of delta function. Think, okay. This is nothing, or this can be written as some d omega by 2 pi e to the power minus pi omega t minus So this is an oscillatory function, but it has a very large peak. So this is the integral representation of delta function. So now if I put this over here in this equation, okay, if I put this, then what I get? Then I have my G, which is R minus R prime and T minus T prime. This will become an integral minus infinity to infinity. Okay. T omega by 2 pi e to the power minus I omega T minus T prime. And the other one, this delta R minus R prime, that, remember, is similar to the three-dimensional Green's function, right? So it is like the Green's function has two parts to it. One is the three-dimensional part, and one is the extension with time, which we have written like this. The total thing is, of course, an integral of these two together, is convoluted together. But I can write down this three-dimensional part, which is just depends on my R. I can write it down like this. So once I write down, I can find out. This is, remember, I can write down as a function of R minus R prime, where now this is just like a solution to the three-dimensional Green's function. So this thing comes from this solution, which is the squared squared plus omega squared plus c squared. Okay. G W R minus R prime is equal to 4 pi delta. So now you see that why this solution over here is just like the three-dimensional Green's function solution that we introduced when we did three-dimensional Green's function. This is because in the static limit, right? Remember, now we have time, so it's dynamic. So you have to compare with the previous electrostatic case. You have to go to the static limit. Okay, the static limit. This goes to 0. Okay, and then what we have is basically we have 3D. Now, the solution to a 3D Green's function, so in the static limit, the solution to a 3D Green's function is basically the Coulomb potential. Solution to 3D Green's function is Coulomb potential. Okay. Therefore, if I put this equal to 0, okay, so the static limit, the solution is nothing but the Coulomb's potential, right? R minus R. So now, to progress more, we want to make one more, not assumption, but one more thing is that since this only depends on the separation, okay, so of the two coordinates, the source and the field, we can basically say that the source is at the origin. So we can take our XYZ coordinate and just put the source at the origin. So we can say that my R prime is basically 0. So there is no loss of generality in that. So since this solution depends on r minus r prime. Okay, we can put r prime is equal to 0. Okay, this is what we can do. And then what we have, if we do that, so then it's a spherically symmetric solution for GW, right? So once we do that, then we have a spherically symmetric solution for GW. Okay. Now, why do we wanted to have this spherically symmetric solution for GW? Because if it has spherical symmetry, then it becomes easier for us to choose what would be the functional form of the grad squared. Because you can write down the grad squared in spherical coordinates very simply. Okay, so you can choose so we can now choose spherical coordinate system. Okay, and that basically in the spherical coordinate system, this grad square is basically just 1 by r square ddr of r square ddr, right? So this is basically, oh, this is basically 1 by r square ddr. So now we can put this back in the equation above. Okay. So now we put it back in the equation above. Okay, so back in this equation, right? So then let me write it down. Then we have, okay, for r greater than 0. Right? So basically the r prime is at 0 at some other r. I have 1 by r squared ddr r squared ddr. Okay, excuse me, plus omega squared by c squared. So plus omega squared by c squared. This whole thing is working on GW of r is equal to 0. Right. Remember. So this is subject to the boundary condition of the point charge at the origin. So if I have a point charge at the origin, then this is for the horrible handwriting sometimes. Boundary condition of point charge origin. Because remember, Green's functions are always for point charge, and over here we have chosen the point charge to be at the origin. Okay.
So why is there no delta function on the right hand side?
If you have a point charge at the origin, what will happen? It's only there at r equal to greater than 0.
Okay, okay.
Yeah. So now we want to integrate this. So which one do you want to integrate? So you want to integrate this equation. You want to integrate this equation. this answers your question. Basically. Okay, so you want to integrate these equations. So let me write down something for this. Say, let's say, let me call this equation B maybe. So let us now integrate equation B, okay, over some sphere which will have some radius r0, but we'll make it vanishing so that it becomes at the origin. Okay, over a sphere of radius, let's say r0, which can go to 0. So it's a vanishing radius r0. So once we do that, the RHS, if I integrate the RHS, where is it, equation B? The RHS is just 4 pi, right? So your RHS is 4 pi. RHS of equation B. Let me write it down clearly. RHS of equation B. This is 4 pi. I want to look at what is the LHS. Okay. The LHS is, remember, the divergence of this becomes a surface integral. Yes. I'm going to write down R to show that only radial dependence is there. GW. This will become minus. There is a minus. There is a minus sign over here. So this is minus. This is minus. This is minus. That's 4 pi r square. And over here, I have used the radius.
So you are doing this on the static limit.
No, the static limit gave us what will happen when we have W equal to 0. Yes, and then we'll see what happens. Just give me a moment. We'll put in the W dependence after this. We'll put in the W dependence after this. So this will have a DDR of and as I said, we want to go to the case where R0 goes to 0. So this is R0 going to 0. So now this 4 pi and 4 pi cancels because both the right hand side and left hand side has 4 pi. And what we get is this relation minus R squared DDR of.
Hello, sir.
Yeah.
So in spherical coordinate, the grad can be written as 1 over R del.
That's what you have done, right?
R into del R, right? Or 1 over R into del R. You cannot simply written grad as del R. There should be a factor there, right?
The radial part is 5. That comes in the spherical part.
Exactly. Yeah. Just check out your exactly del grad in coordinates and you'll find this is there. Going to 0 and this is 1. So you get this relation. It's quite nice the way it goes through. Okay, so this has sort of a vanishing volume integral as your R0 goes to 0. Now,
Sir, where is omega?
where?
Where is omega dependence? There should be omega square by c square, right?
It will come. I'll come to it. The omega dependence will come. Now, you're right. There is an omega dependence. So where is that omega dependence? What's happening with this omega dependence? Right? So there is a, as you rightly point, there is an omega squared by c squared in the differential equation, right? This does not contribute. Why doesn't it contribute? So look at this term. Okay. So I have to go back and forth. So this part, okay, this part. Omega squared by c squared.
Yeah, we will do the integral and take the limit. It will become 0 in that limit.
This is goes as 1 by r. Okay. As r goes to 0. So this has vanishing volume integral. Okay. As r naught goes to 0. Okay. So that does not contribute. Now, let us make one more change of variable. So we have made like a couple of change of variables. We will make one more change of variable, and then we'll go back and redo all these things. Okay. So let us make one more change of variable. So let us go to this equation. Where is this equation? To this equation. Okay. And let us write down this GW that we have. Let us write down as 1 by r. So go to this equation. Let me call this equation C. Go to equation C. I will put this note so that you can look at this notes. Okay. Go to equation C and define a small GW. So how will I define a small GW? I will say GW. I will define as 1 by r GW. So once we do that, then what you see that we get a simpler differential equation. So what we get is d squared dr squared plus omega squared plus c squared GW of r. This is equal to 0 for r greater than 0. So what we have done over here to do this, we use these two things. So we use the fact that if I write down my, so remember this was in terms of, this had an r squared big GW, right? This thing I can rewrite it. So I can write down as r squared ddr of this becomes r ddr of GW minus GW, and this thing r squared ddr of this becomes 1 by r GDR of small GW sorry. 22. Like that, I think I've written it correctly. R two dr so this is what you have used. So you get this equation. Now these kind of equations you can solve. You can solve this equation. So you can solve this equation, and it has a general solution, right? So solution or a general solution of this equation is basically, you can say that let us take my GW to be, so you use a solution and then we see whether it makes sense. Okay, so let's say we take the GW to be e to the power plus minus I omega r by c. So this kind of solutions you must have seen many times, do electronics or couples equation solutions. This is. Okay, so now I'm going to put this back and get the big GW, because the big GW, if I know the small GW, I know what is the big GW. So then my big, so by the way, I keep on saying W and none of you wanted me out, and I do this time, we do this every time. What I mean W is basically omega. Okay, so it's not W. It's T and omega, it's frequency part, the spectral part. Okay, it's omega. So big G omega is equal to then some constant by R e to the power plus minus I omega R by C. Okay. Now if you look at the boundary condition, okay, what was the boundary condition? The boundary condition was this. Look at this boundary condition. So let me call this equation D. If you're writing these things down as I write it, then it's easier for you to go back and forth. Okay. Equation D, that tells you that C is equal to 1. Okay, so you put in the boundary condition, you'll find that this C is equal to 1. So therefore, I have a solution for GW R minus R prime, which now you can see is this. R prime, okay, e to the power plus minus I omega R minus R prime by C. So once we know the radial part or the R dependence of the Green's function, we can write down the full Green's function. The full Green's function was an integral of this over the exponential in t, right? So therefore, now I can write down my G R minus R prime T minus T prime. This is basically T omega by 2 pi 1 over R minus R prime, then into e to the power plus minus I omega. So now let me write it like this, or hold on. So let me write it carefully. Okay. Then that is plus minus r minus r prime by c minus t minus t.
Sir, it's actually mod r minus r prime.
Ah, that's right. Okay. When I wrote right here, you're right. It is. This is mod. It is not bracket in that sense. So I can write this down like this. This I will going to. So now look at thing over here. This actually looks like the integral version of a delta function. Right. So if you look at the integral version of the delta function, which I wrote for that t as one dimension, this is like an integral version of the delta function. So I can write this actually as I can take this r minus r prime mod outside. Okay. And then I have a delta function, which is plus minus r minus r prime as I said mod by c minus t minus t prime. This g, as you can see, this four-dimensional Green's function is non-vanishing only for specific connection between t and r. So this thing, this g is non-vanishing. Okay. When my t is equal to t prime plus write it separately. So once I finish it, then I'll talk. So t prime 1 by c r minus r prime. Okay. And
So this is the
this is one part.
retarded Green's function, right?
This is the retarded Green's function. Exactly. Exactly. So I should write this line later. Hold on. I think I jumped one line. So let me first disturb it. So over here, as you can see, there are two choices, plus and minus. Okay. So if we choose plus, then we get the retarded Green's function. Okay. And this one, as I said, is non-vanishing. So this is non-vanishing for t equal to t prime plus 1 by c minus r prime. So if we look at this, remember prime is at the source and unprimed is where you want to feel it. So the time coordinate at where we are getting the effect is after the time coordinate. So the time coordinate, the source is previous, the time coordinate at the effect is later. Okay. So whatever happens at the source, the signal propagates at the speed of light. Okay. So things happening at the source at prime, t prime, whatever is happening, that you get to know, get to feel at a later time t. Okay. So that's why it is called a retarded thing. If I have taken the minus sign, then instead of a retarded Green's function, we would have got an advanced Green function, so opposite. But in that case, what happens is that the source is getting something before whatever is causing it. Whatever is causing it is after. Okay. So in a sense, that is unphysical. Okay, because it does not respect causality. So simple ideas of causality. So we're not going to use the advanced Green's function at all, because that violates the simple notion of causality. What you are feeling did not happen due to something happening earlier. What you're feeling is you're feeling it for something that will happen later. That doesn't make basic sense. Although, I mean, these things are used. I mean, advanced Green's functions are also used later at certain mediums. We're not going to do that at all. What we're going to do is only the retarded Green's function, where we choose the plus sign. Okay. So on the plus sign, you get this important relation between t and t prime. Now, once we have this, then we can go back and write down the equations that we had for phi and a, right? So your phi and a, go back to the first equation. So now we submit this in the first equation. So now substitute in the equations for phi and a. Okay. So your phi, okay, as a function of r and t. Remember, it has two integrals. There's a d cube r prime, dt prime. Then this Green's function is only using this plus sign. So it will be delta of 1 by c r minus r prime minus t minus t prime over r minus r prime, then rho r prime t prime. And similarly for a is exactly the same. Exactly the same, it is 1 by c c j prime t prime. So if you integrate this, okay, if you integrate this over your t prime, so now if you integrate over t prime, okay, and remember you have to use this condition because this is the condition in which this is valid. Then what you get is phi rt, the integral over d cubed r prime 1 by r minus r prime and rho at r prime t minus c and a at and t is written same time 1 by c j r prime t minus 1 by c. So what you are seeing is that your potential at the time t is due to whatever the charge was at a previous time, okay, wherever it was at a previous time, where this relation between the present time t prime and the previous time has to be governed by this t prime being t minus 1 by c r minus r prime. So you are getting the potential, both the scalar potential and the vector potential at some point in space and time due to whatever was the charge and the current density at another point in space, but at a time which was earlier. So if you remember these equations, this is nothing but what you had derived previously or you found previously as your Leonard-Wichet potentials, right? So this is what, when you did radiation, what we got was a Leonard-Wichet potential. So these are the Leonard, L-I-E, Leonard-Wichet chart. Okay. So these are the Leonard-Wichet potential. Of course, what you have probably done was you have a charge moving and you calculated what is the potential at a distance. Okay. If you get this phi and A, you can then actually get the E and B by using the Maxwell's equations, the equation between A and B and phi and A and B. So use these equations to get it. So over there also the same kind of retarded time will be there in the fields. Okay. Now I have done this for a general distribution of charge and a general distribution of current density, charge density. You have, as I said previously, done it for point charge moving somewhere. I think in Griffiths, you do this point charge moving and you find out what it is. Okay. So over here, why don't you take these equations and try to write down the equations that you had over there. So let me give this as a homework. Okay. Give this a homework, and this homework is already there in the homework assignment that I uploaded. So the homework is, okay, so let me give you your charge density. So your charge density and current density. Okay. This thing, this is for a point charge. Okay. So this at R prime, whatever, R and T, doesn't matter. This is for a point charge. So point charge basically means this will be Q, okay? And so 1, and this is E of T. And then there is a delta R minus R of T. So this is a point charge that is moving along some trajectory, okay? So for that, show that is very easy problem, that my phi RT is equal to Q divided by R minus R of T, this thing, okay. Minus R minus R of T could be some T prime actually. Yes. Yes. And your A of T T T prime by C. So this, which you have typically,
Sir, R of T.
where is R of T?
There should be R of T. In, where you have written R of T prime.
No, this is R of T prime.
Yes, sir, right.
It's not R of T. So this typically you have actually seen as your linear differential potential when you do it in your undergrad or the first year. Okay, we typically don't do it by Green's function. Okay, so that was that was the Lorentz gauge Green's function equation that we showed and we solved it, and found that we can get this retarded and time, and we get this potentials, and from there we can find the fields. Now, what we want to now do actually, and I don't want to start now, is starting from these potentials and fields, we are going to, so Jackson has a nice treatment of this, except I hate the way the symbols sometimes are used in Jackson. Somehow I just don't feel, this. So Jackson uses this kappa and stuff like that, but we are still going to do it. So we are going to write down this phi. Okay, so Jackson writes down phi as, so uses symbols like this. We'll do this next time. So Q by kappa times R, and then retarded. So this kind of symbols Jackson uses to write this equation that I wrote. Okay. And so your R is basically, big R is basically the small r minus RT that I wrote. Okay. The kappa will be something else. So this kappa is basically will be in terms of which direction you're looking at and which is the direction of the velocity. So you can look at it up in Jackson. But we're going to go to this kind of formalism and write down the E and B. And then without doing much mathematics directly, we're going to talk a little bit about what kind of physics that should be there. What is the general properties of this kind of radiation fields? Why do we call it radiation fields? How different this is from the other fields that we have used before? And then we'll sort of try to proceed and go ahead. So I'm not going to do anything right now. I'll just stop over here because we have like 5 minutes left. Okay. So next day we'll continue from over here.